I'll just introduce myself while Matt's pulling up the presentation. So my name's Jesse Clarke. I think most of you were here in the first seminar, right, earlier. But Jesse Clarke, Building Science Manager for Australia and New Zealand. I work for Pro Clima. And I'm going to present some information, but that's interesting, John, your questions around the relationship between European details and different parts around the world. But I guess from my perspective, what I want to focus on is what are the forces that are driving, or what do we need to focus, what do we need to look at in terms of the forces and what's happening on a Windows system and integration into the building envelope that makes it work. So then from that, I'm not going to stand up here and say this is the golden solution that works, if that's what you're looking for, but more understanding how you can derive your own solutions. And a lot of testing, some testing I'll show what we've done in Germany around sealing windows into the reveals. Just use the mouse, Matt, yeah. So essentially window connections, how do you connect that window into the structure and how do you get that to work? So from a moisture perspective and thermal perspective, and a lot of things Hartwig's touched on, and I've got some slides showing a very similar approach, but to kick it off, basically, yes, drainage is important, getting the water out of the structure. So Pro Clima has some systems that are designed to prevent moisture getting into the structure. How you then deflect that moisture or the rain off the cladding systems is very important. So drainage planes and getting the water out to the outside of the structure is very important. All the systems that we do are the secondary barrier. So they're not the primary barrier, but they should be the secondary barrier, but they should be 100% waterproof. So it's an insurance policy to not get water into that structure and allow the structure to dry out. So essentially your house is your castle and you want your castle to work. You build this for your family, you build your homes for your family and you want to protect your family. And that's what it's about, having a healthy, safe and durable structure for people to live in. So the enclosure sits there, you have a building, then you have the elements that go into the building. So you've got the systems, the construction systems, and hopefully you've layered them all right so that the system will dry out. And you have these forces acting on the structure. You've got physical forces, you have temperature forces, thermal, and you have wind and rain forces on that structure. And you have to deal with all these in the building envelope, but then you've got all these additional micro things happening within the structure itself. So you've got moisture flows and you've got thermal flows, which all affect the hygrothermics or the thermal dynamics and the moisture flows in that structure. So we need those structures to be able to handle moisture. They need to handle the external moisture and the internal moisture, which is built into the New Zealand regulations in some respect. So understanding the fundamental principles helps us design systems that work. So in terms of a wall structure, it has to do exactly the same things as a roof structure. And you've got all these things acting on it. So vapor diffusion and latent heat and long wave, short wave radiation, all these funky physics things happening. But so driving rain is very important for window installation. You have wind pressure is fundamental. So wind is actually what drives, well, physical forces on the window, so it doesn't fall out, obviously, but then also water leaks. So managing wind loads on and around the window installation is very important. Sound, windows, systems also have to manage sound. Self-weight, so the whole structure has to stand up, obviously. We have large temperature differences. So in summer, in particular, you can get very hot external claddings, external temperatures and large temperature differentials. So you have diurnal swings, very hot during the day, 60, 70 degrees, and then it can go sub-zero at night. So the structure has to be able to handle these temperature swings. Fire properties are important for the building code. Air infiltration, so this is from an energy perspective and managing that air infiltration so you don't get energy losses or energy gains depending on what season. Movement of the frame, also important because then that's when things start to fail. So if you get moving structures, then things crack up and you get failure of the systems. And building movement. So when you get, well, as you know, earthquakes, things move and things break. I don't think I need to tell you that. I'm from Australia. You know more about that than I do. And then moderate temperatures, so just the internal temperatures and what's happening on the inside of the structure in terms of those internal temperature day and night. And obviously water vapor, which is a big thing that Pro Clima is about, managing that water vapor, managing water vapor getting into the structure and allowing the water vapor out of the structure, so the drying capacity of that structure. So if you take all those things that the wall system's doing, we need to then put that into that junction, that connection between the window and the wall structure. So we need that little gap to do all those things that the wall system itself does. And we want it to be as high a performance as the wall system if possible. So how do we get that to work? We need to make sure that the products we use and the workmanship are of high quality. So looking first at the actual window system, in terms of managing this issue around moisture, we need to look at what sort of framing systems and glazing systems we're using. And as you know, if you use double glazing or high performance glazing systems, then you're going to keep the internal surface warmer, and that's good from a condensation moisture perspective. What you're seeing there, so thanks to Technoform for supplying this, but the unthermally broken aluminium frame gets very cold. So if we're not using decent window frames, we'll get very cold internal surfaces, and that's potentially a condensation problem. You get wet window frames, condensation forming, and that ultimately results in mildew or some sort of mold growth. So if we start moving towards higher performing thermally broken window frames, this critical line here we're looking at basically a condensation point along the window. And then if you use better frames, then that condensate point moves in and you don't get that cold internal surface, so you prevent the condensation from occurring. And then of course going to super high performance frames and triple glazing units, which are even better. So if we got this high performing window system, air leakage. Yeah, air leakage is a big issue. So obviously the window systems have to be air sealed as well. So you don't want air leaking through the window frames and through the seals and gaps around, and how the seals on the sashes that seal into the window frame itself. So it's very important to have well air sealed window systems. And then the thermal breaks in the glazing are very important. So this is showing an aluminium thermal break in a double glaze system. Sorry, aluminium thermal break in a double glaze system, where you get higher conductivity around the perimeter and you end up with this often amount of condensation occurring around your double glazing window. And this is because it's basically got crappy aluminium around within that glaze unit itself. Versus a high performance, low conductivity spacer within the IGU, then you get that line, bring it back in, and you don't end up with that condensation forming around your IGU. So you should be using low conductivity spacers within the IGUs, or at least asking your manufacturer to put them in for you. So, sorry, warm edge spacer versus an aluminium spacer. There you go. And then once you've got your high performance windows, there's no point in installing them incorrectly. So this is showing a relatively typical installation detail for an aluminium frame, and that's the internal window sill, which hangs right outside the building. And the frame, aluminium, is going to get very cold, and you've got this huge cold surface for condensation and moisture to accumulate on. The only good thing I can say about that is it probably draws out a lot of moisture out of the internal air and dehumidifies, but that's probably not the best way to do it. So then you come down to that scenario where you've got the window hanging right out with an aluminium, which is not a very good solution at all. So how should we position our windows? And Hartwig went through this, but just to recap, if you got your wall there, it doesn't matter what this is, it's a big chunk of wall. So let's just say it's an insulated SIPS panel for argument's sake. Then if you look at isotherms through that, you've got outside and inside, and you look at the isotherms through that, what I call is happy isotherms. Happy isotherms is when they're all separated, evenly distributed, and they don't cross or go near each other, and you don't get this weird effects happening. So they're still happy isotherms when you put your window in the middle. But you can see what's happening there is that the window is actually creating a thermal effect, and those isotherms are then having this break in the isotherms here. It's hard to avoid that. Then that's when you start getting into all sorts of details around window junctions and organising the insulation layers such that you can optimise that for thermal performance. So then you say, well, okay, what Hartwig was discussing, you change the location of those windows, put it on the inside, then you've got this scenario where you've got this cold internal surface and it gets nowhere near as good performance. Then you say, well, okay, put it on the outside, and you've got this cold spot in the corner, as Hartwig mentioned. So then you go, well, obviously the best place to put it is in the middle. So how do we get window details where the window goes in the middle of the insulation system, of the insulated wall section, depending on how you make that? I mean, it could be anything, but it just has to sit in the middle of the insulation section. So, as I said, all sorts of details and ways that you can address that, and Europe's gone far further down the track of looking at that and the exterior insulation systems and how you wrap them in. But we obviously have different construction practice here, a lot of lightweight timber frame, and that gets back to the EAF systems and how the US suffered their water ingress and learning from the US and Germany. So how can we take the guys over here from North America, learn from them as well, and get those details so that we can manage that thermal performance, but also the moisture ingress. So fundamentally, air and moisture are interlinked. And air and moisture are interlinked because basically you have humidity or moisture in the air itself. And if you have air leaks around your window, it can carry moisture with it. So when you have air transferring, cold air transferring from outside, and it cools down an internal windowsill, you can end up with cold spots and then high moisture content in the windowsills, which then turns into mold growth and long-term durability issues. So that's a bad thing. And that's just an example. Again, this is a German windowsill, but it's an air leakage problem that's cooling down the internal surface, resulting in mold growth, or you can see a bit of stain in there. Then you've got it going the opposite direction. So you can end up with warm internal humid air from the building going the other direction and leaking air through around the junction point, and then you end up with potential moisture accumulation, rot and mold, and damage to coatings or render on the outside of the structure. So there's some more staining on the external side of the structure there. Oh, that's German. Basically, positioning the window. So we've talked about that, but how do you position that window, but also seal the window in? So we're talking about the window should sit in the middle. Yes, it can go on the inside and outside. Optimum is in the middle. But those sealing systems and the air sealing weatherproofing systems to get the window to work from an air leakage and water vapor transfer perspective. So Pro Clima has some taping systems that go around the windows. They can be installed in different manners, different methods, depending on whether windows already in the system, and you come along and retrofit the taping systems after to create an airtight and airtight and vapor control seal, and systems that actually tack onto the window, that you put onto the frame of the window before you insert the window into the window reveal, and then it tapes down. And these two systems are examples of that. So ideally, those window systems, that then enables you to put the windows in the center of the wall or insulation layer. So we've undertaken some testing at IFT Rosenheim in Germany. So that's the Institute of Fenestration Technology. Institute of Fenestration Technology in Rosenheim. So they're one of the world leading research organizations for window performance. And we tested it in the weatherproofing rig. And the idea there is that you put basically water spray onto the window and you apply a pressure. You apply the pressure, and that basically induces air leaks around any points in the window. Air leaks are then what induce water leaks through any construction system, but in particular around windows. So if you have any air leaks, then there's potential water leak under wind, driving rain conditions. So the thing that we found here is that when we tested it, we took the pressure up, and you take the pressure up from 0, and we went through this sequencing, and it went up and up and up. We took it up to 600 pascals. But the interesting thing here is that flow rate, the air leakage through the gaps around the window, stayed at Zero. So it's essentially a perfectly sealed, air-sealed system. If you install those tapes with good workmanship, good quality products, you get a perfect air seal, you get a perfect watertight seal. So you can't get water going in around that window system. So this is the seals around the, the gap around the window, and they were all taped up. I'll just move through, taped up on the inside and the outside, so the flashing tapes around the outside to seal those windows in. There's the extra seal product taped up and sealed onto the window. And that pressure there, sorry. What we did there is we took it up to the test pressure and we went, well, okay, well, let's see what happens. When we're not getting any airflow, it's a bit boring. Tests that actually pass, systems that pass tests are really boring. Tests that fail are really exciting. It's a bit like a Mythbusters. If it doesn't fail straight away, see if you can make it fail. So we took the pressure up and up and up and up, and we took it up, and the window itself started leaking. So we had to gunk that in, but the seal around the outside wasn't leaking. The window there, you see the water leaking around the window itself, but not around, it wasn't coming from the seal around the window. And the pressure we got to was 2,000 pascals, so 2 kilopascals. The regulations, I think I have in here, I'll state what that is, but so they're the taping systems, and they all stayed in place, and they maintain that airtight seal up to 2 kilopascals. And 2 kilopascals is a lot of pressure. Is that a lot of pressure? Yeah. So would that pass everywhere in New Zealand? Yeah. So on altitude or building height? Yeah, the building height. So when you get really tall buildings, you get higher pressure. And this is a problem we're seeing in Australia as well. People are using residential window systems or window systems that are rated at residential pressures. The residential test pressure is about 200 pascals. We were at 2 kilopascals, so 2,000 pascals. So those window systems measured at 200 pascals in Australia. People go and put them on high-rise multi-res and then wonder why the windows are leaking water through into the internal space. Well, because they weren't rated at such high pressures when you go up into taller buildings. So the regulations require 600 pascals in Germany. We took it up to 2 kilopascals. So we went way above and still got zero air leakage through those, through that connection point around the windows. So that's it, that's the last slide. But fundamentally, you air seal a window in, it's gonna be weather tight. So then it comes back to those details around, well, are you using a solid masonry German style system that's insulated? Are you using a lightweight timber structure? Either way, it has to maintain those air seals under all the movements and forces of temperature and temperature cycling. So the durability of that window install is dependent on how long you can hold that air seal for. And then obviously the drainage, flashings and detail to get the water to the outside is fundamentally important. Yeah, thank you.